Hi, everyone. I hope you're doing well. This is the last lesson of our third unit, lesson 6. Today, we're going to talk about the expected value in probability situations. And let's just take a look at an example, and hopefully, some of this will seem intuitive and it'll make sense as we go through. So, imagine you tossed a coin 100 times. So, two-sided coin, heads and tails. How many times would you expect the coin to land heads? So, how many times would we expect it to land heads? So, 100 times, you know it's a 50-50 chance. You would expect, probably on average, to get 50 heads, also 50 tails. Would you be surprised? In part B, it says, would you be surprised if the coin did not land heads that many times? And probably, hopefully, you say no, because this is a random chance, right? In fact, it's probably unlikely to land exactly 50 times and be heads, but there is a chance, and on average, we would say it would land 50 heads out of 100 flips. So no, because there's a random chance of landing heads. And that randomness means that you might, get 45 heads, 55, whatever it might be in between. That introduces this concept of a probability distribution, which we'll talk a little bit more about next unit, but today we're going to focus on this thing called the expected value. So if we extend this concept into another situation, imagine you rolled one six-sided die 60 times. How many times would you expect the die to land on a 6? So land on a 6, so there's 6 sides. And we're rolling it 60 times, so if you think the probability of it landing on a 6, really that's 1 out of 6. And you might intuitively just come up with the answer here. And hopefully you're thinking, well, if it's a 1 out of 6 chance and I roll it 60 times, I'm going to have this thing land, on average, 10 times to be a 6. But what's happening in both of these situations? The previous question and this one. This is what's called the expected value. And expected value is denoted by this E, with the X being the random variable that we're talking about depending on the situation. So if I was flipping a coin, that random variable would be the outcomes of the coin. If I was rolling a die, it would be the outcomes of rolling the die. And what we're doing is we're taking the total number of trials. In this example, there was 60. In the previous one, there was 100. So we're taking the number of trials, which we often call n, and we're timesing it by the probability. And so in this example, I've got 60 times 1/6, which just gives me 10. This is what the expected value formula is for a situation like this where you're looking at one specific outcome. So down here it says, if there are n trials of an experiment and an object or event rather has probability of p occurring in each of the trials, then the number of times we expect the event to occur is just that formula. So E of x equals n times p. So pretty straightforward, and that can come up in a lot of different situations. And it's not too complex, but let's just take a look at a couple. So the first one here says, each time a soccer player kicks for the goal, he has a 3/4 chance of being successful. And in a particular game, he has 12 kicks for goal. How many goals would you expect him to score? So we've got define our N and our P. Keep those in mind. So N is the total number of trials. So in this case, we've got 12 kicks, and the probability obviously will be 3/4. So my expected value, E of x, will be n times p, of course, which is just 12 times 3/4. And you can punch that in or work this out. What's 3/4 of 12? 9. So we expect him to score 9 times. Another example, in his basketball career, Michael Jordan made 83.54% of his shots from the free throw line. If he had played one more game and had 18 attempts from the free throw line, how many shots would you expect him to have made? So again, N in this case, and P. So N is our total number of trials, which is 18. Our probability is 83.54, but remember we're always converting that to a decimal from percent. So I just simply divide that by 100, which becomes 0.8354. And then my expected value is just those numbers multiplied together. So 18 times 0.8354. And you can punch that into your calculator, or you can just get this answer off me, and you get out to 15.0372, which obviously is not making a fraction of a free throw, so we can round this to 15. So 15 free throws. So we're going to extend a little bit beyond that concept, but we can take an example here to help illustrate a couple things. So this one is more of an application of what we're doing. So imagine you're playing a carnival game where you roll 2 6-sided dice. And if you roll doubles, you win $10. And the game costs $2 to play. Doubles, just so we remind ourselves, doubles is just when you get the same number on each die. So this is the same number on each of the dice. And so the probability of that, so you would have like a 1 and a 1, a 2 and a 2, 3 and a 3, and so on. Here's our little sum table. So 1 and 1 is this, a 2 and a 2 would be this. In fact, you get this happening 6 out of the total of 36 sums possible or outcomes possible. So the probability of doubles, just so we all have the same idea here, is going to be 6 out of 36, or just 1 out of 6. So the first part here says in part A, if you play 12 times, how many games would you expect to win? So obviously we've got an expected value question. We're expecting how many times to win. So our total number of trials here, so I've got n times p, we're playing 12 times, so 12. And our probability of winning once is this 6 out of 36, or 1 out of 6. And so we can work out a little bit of math here. This would be 3. That becomes 6 over 3, which is just twice. So we would expect that if we played 12 times, we're going to win twice. So part B, would you expect to win more money than you lose if you spend all your money? It's a bit of a thinking question. So if I'm going to spend all my money, and what do we have to start? We've got 12 times. So my expected winnings. So my winnings will always be the winnings minus whatever the cost is to play. And we know this cost to play is $2 each time. And the winnings, in logically here, if I'm going to play 12 times, we said I expect to win twice. And my winnings will be that 2 times whatever money I'm going to win, which in this case you're expected to win 2 times and $10 each time. So I got 2 times 10. Minus the cost to play, so this is kind of its own thing there, and then my cost to play, I'm going to play 12 times and it costs $2 each time. So I work this out, I get $20 minus $24. So I get a minus $4. And you can put your dollar sign either in front of or in between the negative and the 4. So in the end, therefore, we would expect to lose $4 in 12 games. So not a bad ratio, but in the end, I would say that we're going to lose more than we're going to win. So this situation described above involves using expected values, and it includes monetary values as well. So we're assigning values to these things. The next part we're going to look at with expected values is when you have multiple outcomes. And this applies in a lot of different situations. So we said expected value we're denoting as E of X is the predicted average of all the possible outcomes of a probability experiment. This can also be thought of as a weighted average, and it's generally used when the weight of a probability is not the same for each outcome. They could be, but it doesn't have to be. And we'll look at a couple different examples. We can calculate this by taking each outcome, let's call it x, and we multiply it by its relative probability. And then we add them all up. And that's why this is sometimes called the weighted average or the weighted probability, because it is the same formula as a weighted average formula. So I'll show you the formula here, but really applying it, I think you'll understand a bit better. So we've got the expected value is equal to each outcome, so x is the outcome, times its relative probability. And I add that to the next outcome times its probability, and I just keep adding these together so I get an overall expected value. And of course this formula is given, so you don't have to memorize it, but it's more of a logical thing anyways and maybe easy to remember. Let's take a simple example where we can apply this. So this one, it says we've got a spinner is spun and players are awarded the points displayed below. On average, how many points can we expect to be awarded? So when I look at this, it could land a 5, a 10, a 15, and a 50. And it appears the spinner is split perfectly in 4. So I would assume the probability of each of the 4 segments will be the same as each other. So they're all the same, and that would be 1 out of 4. So I can think of this as the expected value. Now, if I was just to look at this and say, okay, well, on average, how many points would you expect to win? You have to think of the on average part. Like if I was to spin this thing 100 times, what's the average outcome that I'm going to get? And that's where it's kind of like a weighting. And so the weighting is determined not only by the probability, but also by the amount of points that you get for each outcome. So it would be hard to guess the answer to this without actually making some calculations. So I'm going to take each outcome. So the first one is the outcome of getting a 5. And I multiply it by its relative probability, which would be 1/4. So this is my outcome, is the 5, and then the 1/4 is my probability. And then I would add it to the next outcome, which will be 10, let's say, times its probability. And so here I get it. And notice all the probabilities are going to be the same, which is fine. I keep going, 15 times 1/4 plus 50 times 1/4. So they are all weighted equal. And so you could make this calculation a bit simpler by just saying it's 1/4 times 5 plus 10 plus 15 plus 50. Or you could take the long road, but this one's a bit quicker. And so you end up with 1/4 times 80, which just comes out to 20. So what does this 20 represent? So you have to think, if I was to spin this thing a lot of times, on average, if I was to add them up and take the total number of spins, on average I would get around 20 points. Even though 20 is not one of the outcomes, it's the predicted average that I would get. So therefore, the predicted average number of points for each spin is 20. Like that. So this one, really it's called a uniform probability expected value because the probabilities were all the same. You don't necessarily need to remember that, but it makes it a bit easier in your calculations. Let's take a look at one where it's not uniform. This one says the following table represents the number of donuts purchased by customers at a donut stall and the associated probabilities. Where would they come up with these probabilities? Probably just from, taking a count of all the people that come in. So it's actually kind of a percentage as well. And we've talked about how those are somewhat synonymous. So a percentage as a decimal. So we got people who came in and bought 1. There's a 23% chance, or 23% of the people did that. People who came in and got 2 is 38, and so on. So the first part is find the value of A. And IB likes to throw these ones in. So A is located here, obviously. And we have to use a concept within every probability experiment. What do all of the probabilities add up to? So if you were to take 0.23 plus 0.38 plus A plus 0.13, this total will always be 1 because it's 100% of all of your outcomes. So A, we can think of by adding these all up. I know it's going to be 1. And so you can just rearrange this. So A is equal to, and I'll just do this kind of quickly, and all of those add up to 0.79. So that makes A 0.21. So 21% chance that someone purchases 3 donuts. So in part B, they're saying find the average number of donuts purchased over a long period. This is synonymous with the expected value. So how many donuts would you expect over time, on average, people to purchase? And again, just looking at the numbers, it would be hard to predict. But if you kind of look at it, you've got 0.23 and 0.38. That's a pretty big chunk. So that's going to weight these things closer to that end of the spectrum from 1 to 5 here. So we're going to be closer to the 1-2 range, so somewhere maybe around 2, which is good to kind of predict or try to figure it out. And you look at the other end, there's less weighting with these ones because the probabilities are lower. So I've got expected value. I take each of the values. So the values here in this case are the number of donuts. So I got 1 times 0.3, or 23 rather, plus 2 times 0.38. And I'm just putting brackets to separate them because it's going to be a long equation. You don't necessarily need them. And then we've got this one times what we found for A. And then you just keep going. And you would punch that all in. And again, I'll do it kind of quick. And you get 2.39 if I round it to 3 sig figs. So this is the predicted average number of donuts that would be purchased if you were to have many repetitions or many customers come in. So therefore, the average number of donuts purchased is 2.39. So this scenario, which is quite different than what we started with in the lesson, is when you have all of these different outcomes and they're asking for a predicted average. If I was to just look at something specific, like let's say someone came in, I don't know, 50 people came in, and it was like, how many times would you expect them to purchase 2 donuts? So it's taking all the same information. 50 people came in, and how many times would you expect them to purchase 2 donuts? That's not looking at the overall expected value. It's looking at one specific outcome. And so in that case, you could use the other formula, N times P, if there's 50 people, and I multiply it by the percentage or probability that they're going to do that. I'd take this, and so what's that going to be? 72 divided by, I'll punch it in anyway, times 0.38, and we get 19. Perfect. So you would expect 19 people to purchase 2 donuts. Different question than what we just looked at. Similar, but looking at one specific outcome. So this idea of, especially this one where we had a game, there's something that's called a fair game. And in fair games, sometimes, in gambling, it doesn't have to be gambling, but it could just be fun with points. The expected gain of the player from each game is the same as the expected return or payout from the game. And so a fair game is designed to have an expected gain of 0. So I would say a fair game, just so we have it written down explicitly, is where the expected value is either equal to 0 or where the expected winnings is equal to the cost to play. So they would even each other out. Almost no games involving money have an expected value of 0. They're not designed so that they're fair. They're designed for some person to make more money than the other person. So it's an important concept. So see if you can try the U-Try, and I'll put in some solutions and you can check in the notes in OneNote. And within that is this idea of a fair game. But it should be straightforward, but you can definitely take a look at the solutions. Okay, take care, and I'll see you next class. Bye.